Welcome to Process Control Design and Practice. My name is Tom Meadowcroft. In this video, we will learn about human-machine interaction. Why do we automate processes? The limitations of people and the capabilities of computers. Confronted with the need to react to important but infrequent events, people will become bored and inattentive. A computer will never lose focus. People can be trained, but that training fades, and under stress, many operators will try to improvise. A computer will always follow its procedure. People can take shortcuts, be slow to react, or snooze on the job. A computer will always be attentive and can be attentive in 100 places at once. Computers don't quit, retire, or go on strike, and there's never a shortage of computers as there can be of skilled operators. So why do we employ operators? Well, the limitations of computers and the capabilities of people. A computer will continue to follow its procedure no matter how stupid, dangerous, or expensive those actions programmed into it may prove to be. Operators can evaluate context and intervene. A computer can solve no problem that it hasn't been taught to solve. Operators have a mental model of the process, can evaluate novel situations, and synthesize solutions to problems that the designers did not anticipate. Computer code reflects the ignorance and conservativeness of the engineers who created it. An operator can navigate around the many small problems that the engineers did not plan for. The success of an automated process, therefore, is a function of the quality of the control system design, the quality of the operators and their training, and how well the control system and operators work together. Computer control systems and operators have complementary skills. No system can be completely and perfectly automated. A well-designed control system must allow for and encourage excellent operations staff. This affects how we design graphics and interactive displays, how we implement automatic versus operator interactive triggers, and how we seek the operator's attention and input with various graphics and alarms. So let's look at different types of interaction. We'll start with interlocks. Operators are forbidden to take certain actions, and some automation will take place outside of the operator's control. These interlocks should be put in place because it is potentially too dangerous or costly to rely on an operator's attention, training, or speed of response as determined in a process hazard analysis. That PHA should be a consensus that includes operators, not something imposed on them. And above all, these interlocks and automatic actions should be transparent. Interlock devices should show as locked on screen. Training and graphics should make the operator aware of why they are locked out or why an automatic action is taking place. If a pump is locked because a level is low, it should show as locked, and clicking on the locked pump should enable the operator to see that the low level is the trigger. The capability for that transparency is a feature built in to most modern graphic systems if engineers invest the time to use the feature by writing out a descriptor for each interlock. Normal human-machine interactions are for manual tasks, including infrequent tasks that aren't worth automating, tasks that require people like sampling, special operations like maintenance, or requests to the operator for permission to proceed. If the computer needs to get the operator's attention to do something, it should call their attention in a manner which is obvious but less demanding than an alarm, like a screen pop-up with a beep. The system should be seeking the operator's okay to proceed when the system needs a resource it doesn't control, like a raw material tank. When the operator needs to prepare for something like a sample, or when a significant change is happening to the process state, which the operator should be aware of for the sake of his or her situational awareness. The next form of interaction is parameters. There are three types of parameters. One, safety interlocks and limits, which only engineers with permission and access can change. Two, quality, yield, and productivity settings like chemical stoichiometry parameters and quality set points for separations, unit operations, which require some sort of expert consensus among engineers, chemists, and managers to change. Finally, operation settings like level set points, which of two pumps to use, and various settings to move fluids around, which are the operator's responsibility moment to moment. Other than the type 1 parameters, which should not be accessible to the operators, all of the type 2 and 3 parameters should be changed by the operators, including the type 2 parameters where they need permission and instructions to be able to make the change. So whenever possible, all changes to the automated process should be made by the operator, not the engineer. They own the process. They need to be aware and feel responsible for all of the changes, even if it's a chemistry change that a chemist could only have the authority to make. Let the operator make the actual change once the decision is made, so that they're aware and responsible for the change, and that they can log those changes and alert the other operators. Don't bypass the operators. Finally, sequential logic interactions. As a batch proceeds, each step consists of an action followed by a transition, where the process waits for something before the next action. In an automated plant, a control room operator might be supervising 10 batch operations, 10 units waiting for the next process or time trigger to make a change. It is vital that the operator knows what each of those units is waiting for. Why? Well, first, transparency and safety. Operators need to know if the current state is normal or a problem. Is an intervention required? Second, troubleshooting. Every batch unit gets stuck occasionally because instruments and solenoids and motors and above all engineers are all imperfect. How do we achieve this? Well, displays for batch processes should show which phases are active, ideally in a sequential function chart form. And then each transition of each phase needs a short text message which states what it is waiting for. That text message needs to be written when the phase is written during the design phase, and then it needs to be presented that text message needs to be presented for the operator on the graphic when the phase is executing. This investment in design transparency will pay off in safety and efficiency when the process is operating. We've been talking about messages appearing on operator displays, so let's move on to graphics, or graphical user interfaces. Until 50 years ago, interfaces were hardwired panel boards, but process graphic technology has progressed alongside personal computers, game consoles, and graphic chips. Modern graphic interfaces can be as simple or as complex as any other image on a high-resolution display, which leaves several questions to the designer: plain versus elaborate, 2D versus 3D icons, colorful versus mostly grayscale. Trends and fashions have gone back and forth, and academics love to write papers, most of which miss the key point. The operators are going to sit in front of these graphics for 40 hours a week. Making them happy should be, and probably will be, your first priority. And most control room operators are older people who want simple icons and bland colors that won't give them a headache. So don't worry too much about style and color schemes. Go with whatever the consensus is from the users. Where the engineer can make a real difference is in how the visual information is organized. There are two objectives that displays need to satisfy. One, show the entire process so that operators can scan everything. And 2, provide functional displays to facilitate the tasks the control room operator needs to complete. These objectives are quite different and best solved separately. For the first, put the entire process on a series of big process overview screens. This allows you to display the entire thermodynamic and equipment state, sequential logic messages for batch processes, and process modes for continuous, key trend charts if that is helpful, and color and movement cues to draw attention to trouble when alarms start to sound or process details change. These are not interactive screens. Only the numbers and statuses on them change. They're for viewing, situational awareness, and troubleshooting. A complete set of screens that allow a constant visual process overview is essential for keeping the operator involved, aware, and alert to changes. In this example, there are many motors, valves, and sensor values and statuses. Colors show levels, alarm and device status, and which pipes have flow moving through them. Too much detail? No, not for an engineer or an operator who is used to looking at these screens every day. The next type of graphic is designed for operator interaction. I like to call these human-machine interface or HMI displays as opposed to the process overview displays. Underneath the big overview displays mounted in a control room above the operator will be 2 to 3 smaller monitors with a pointing device and a keyboard which allow the operator to manipulate the process. There will need to be many more HMI graphics than overview graphics to cover a given process, so the HMI graphics should be linked and cross-linked in a menu structure to allow the operator to switch and bring up the particular graphics needed for today's interaction. The focus for the HMI graphics is things that can be changed, like valves, pumps, controllers, buttons, dialog boxes, rather than the process data. Most commercial control systems use Windows graphics with pop-up interface windows and point-click controls that anybody who has used a PC is familiar with. In this example, you see an HMI that represents part of the process on the previous overview that you saw. Each of the pumps and valves can be switched from computer to operator control, allowing manipulation of set points, stop start, and open close status, as long as the device isn't locked out by an interlock which would be clearly indicated for each device. A batch overview would show recipe and phase status messages, and a batch HMI would allow operator interaction with the phase, responding to queries, giving permission to proceed, and showing that what the batch phase is currently waiting on for troubleshooting purposes. Other important graphics are a batch recipe manager, which displays batches as sequential function charts of phases. Very useful for operators running multiple batch units, so they can keep track of where each of their units is in a batch recipe. Process parameter pages with lists of important parameters for a unit in one place, and graphics with access to a data historian, allowing process data to be analyzed by an operator or an engineer for troubleshooting and predictive maintenance purposes. Let's end this lecture here. There's more discussion in the text. Part 2 of human-machine interaction will be a discussion of alarms and alarm management. Look for a full text, exercises, and more videos at chemicalengineeringpractice.org. Find videos on YouTube by searching for Process Control Design and Practice. Like and subscribe. I'm Tom Meadowcroft. I hope to see you again soon.